Welcome. Today we'll solve a practical electrical engineering problem involving a choke coil. We need to determine the inductance required to run a 60-volt, 10-watt lamp on a 100-volt AC supply. Let's start by drawing our circuit diagram. We have our 100-volt AC supply, connected in series with a choke coil of unknown inductance L, and our 60-volt, 10-watt lamp. First, let's calculate the resistance of the lamp. We know that power equals voltage squared divided by resistance. Rearranging this, we can find that the resistance equals voltage squared divided by power. Plugging in our values of 60 volts and 10 watts, we get a resistance of 360 ohms. Next, we need to find the current through the circuit. Using Ohm's law, the current equals the lamp voltage divided by its resistance, which is 60 volts divided by 360 ohms, giving us 1/6 of an ampere. Now we can find the total impedance needed. It equals the supply voltage divided by the current, which gives us 600 ohms. Now comes the key part. In an AC circuit with resistance and inductance, the total impedance forms a right triangle with resistance and inductive reactance. Using the Pythagorean theorem, we can find the inductive reactance by taking the square root of impedance squared minus resistance squared. This gives us 480 ohms. Finally, we can calculate the inductance. The formula for inductive reactance is XL equals 2 pi FL, where F is our frequency of 60 Hertz. Solving for L, we divide XL by 2 pi F. This gives us an inductance of approximately 1.27 henries. Welcome. Today, we'll solve a Young's double-slit experiment problem. Let's understand how to find the distance between the third minima and the central maxima. Let's first visualize the experimental setup. We have a light source, two slits separated by a distance d of 1 millimeter, and a screen placed 1 meter away. When monochromatic light with wavelength of 500 nanometers passes through these slits, it creates an interference pattern on the screen. The position of minima in Young's double-slit experiment is given by this formula. Y sub m equals m plus 1/2 times lambda L over d, where Y sub m is the position of the MTH minima, m is the order of the minima, lambda is the wavelength, L is the distance to the screen, and d is the slit separation. On the screen, we see an interference pattern with alternating bright and dark bands. The central maxima is at the center, and the minima occur at regular intervals on either side. We need to find the distance to the third minima. Let's solve for the third minima. For the third minima, m equals 2. Plugging in our values, we have 2 plus 1/2 times 500 nanometers times 1 meter divided by 1 millimeter. Simplifying this, we get 1.25 millimeters. Therefore, the distance between the third minima and the central maxima is 1.25 millimeters. This means if you measure from the center of the pattern to the third dark band, you would measure 1.25 millimeters. Let's solve a problem about energy stored in capacitors. We have a 600 picofarad capacitor that's charged by a 200-volt supply. We need to find the energy stored initially, and then what happens when we connect it to an identical uncharged capacitor. Let's start with part 1. Here's our initial setup. We have a 200-volt battery connected to our 600 picofarad capacitor. To find the energy stored, we'll use the formula. U equals 1/2 CV squared, where C is capacitance and V is voltage. Let's plug in our values. 1/2 times 600 picofarads times 200 volts squared. Calculating this out, we get 12 microjoules of stored energy. Now for part 2. We disconnect the battery and connect our charged capacitor to an identical but uncharged capacitor. They're connected in parallel, which means the voltage will equalize between them. Let's solve this step by step. First, the total capacitance in parallel is the sum. 600 plus 600 picofarads equals 1,200 picofarads. The initial charge stored was CV, or 600 picofarads times 200 volts, which is 120 nanocoulombs. This charge will redistribute, giving us a new voltage of Q over C total, or 120 nanocoulombs over 1,200 picofarads, which equals 100 volts. Finally, let's calculate the new energy stored. Using our energy formula again with the new values, 1/2 times 1,200 picofarads times 100 volts squared. This gives us 6 microjoules. Notice that the final energy is half of our initial energy. Some energy was lost in the process of charge redistribution. Let's solve a problem involving two cells connected in parallel. We have two cells, one with an EMF of 3 volts and internal resistance of 1.5 ohms, and another with an EMF of 2 volts and internal resistance of 1 ohm. These cells are connected in parallel across a 3 ohm resistor. Let's draw our circuit diagram. Here we have our first cell with EMF of 3 volts and internal resistance of 1.5 ohms, our second cell with EMF of 2 volts and internal resistance of 1 ohm, and our 3 ohm resistor connected across them. To solve this problem, we'll first find the equivalent EMF. The equivalent EMF for cells in parallel is given by EMF 1 times R2 plus EMF 2 times R1, all divided by R1 plus R2. Let's substitute our values. We get 3 volts times 1 ohm plus 2 volts times 1.5 ohms, divided by 1.5 ohms plus 1 ohm. This gives us 2.4 volts. Next, we need to find the equivalent internal resistance. For cells in parallel, it's given by R1 times R2 divided by R1 plus R2. Plugging in our values, we get 1.5 times 1 divided by 2.5, which equals 0.6 ohms. Now we can find the total resistance by adding the external resistance to our equivalent internal resistance. That's 3 ohms plus 0.6 ohms, giving us 3.6 ohms total. Using Ohm's law, we can now find the current in the circuit. Current equals the equivalent EMF divided by the total resistance. That's 2.4 volts divided by 3.6 ohms, which gives us 0.6667 amperes. Finally, to find the potential difference across the 3 ohm resistor, we multiply the current by the resistance. That's 0.6667 amperes times 3 ohms, which gives us 2 volts. Therefore, the potential difference across the 3 ohm resistor is 2 volts.